CHEM766. So the presentation will be by Levi Lystrom, and he will introduce an innovation to the methodology. He will inspect how the dynamics of wave packets differ if you look onto an electron and onto a hole. And he will look how the Coulombic interaction between electron and hole may affect those dynamics. So it is primarily methodological talk, although he also has some applied virtues. Floor is yours.
So I'm going to look at the recombination of photoexcited electron-hole pair. So the system I'm going to be looking at is an iron dimer with Prussian blue. Our methodology can be used on any system pretty much, as long as it can be calculated on. So we can't go to massive systems because we can't get the ab initio local potential. So the methodology we use, we pretty much use the same as everyone else, except we introduce two wave functions simultaneously calculating, and the only way that they are connected is through the Coulombic attraction, which is over there, where this is calculated at the end of every cycle. So it becomes not a static potential, but a dynamic potential. So it goes throughout the entire step, so it's very much like SCF potential. The local potential that our total potential is the local potential plus the Coulombic potential. The local potential is shown there, which is abstracted from ab initio calculations performed in VASP, and it is collapsed into one dimension through integrating over the x and z spaces and then dividing, then normalizing it. So this is our potential, where the iron is put about at 6 and the Prussian blue is at about 11. So through that methodology, we can look at rates, and as I talked about in Javeds, I was not happy with the single exponential throughout the entire time scale, and I was also not happy just by looking at the position. So I did it in two ways, finding rates. I did it where I just integrated like everyone else, but then I did the overlap of the two electron and hole, because you would think if the electron and hole are on top of each other, then there's a probability for recombination. So I also did this, and on top of the second method, I looked at the maximum of the overlap, and I calculated the beta final, where the overlap was maximized. And surprisingly, we see that the rate is not exponential when we increase our dielectric constant, because unlike everyone else, I did not do it with initial momentum. I had my momentum fixed, and I varied the dielectric constant, because if you think about splitting your photoexcited electron hole, depending on the medium that you're in, you could have very high dielectric constant or very low. So we wanted to see, because there was a paper that said that this system used to split water has an increased efficiency when it has a polymer matrix involved. And most of our data would support the idea that when you have dielectric constants between 3 and 10, the rate of recombination is the lowest, which would indicate that that would improve the efficiency of the cell.
What is your black and red here? It's your different methods? Or
yes, two different methods. So black is method 2 and red is method 3. Not these methods, the method of propagation of the wave packet. So method 2 is doing a Fourier transform from of the momentum operator from momentum space to spatial space, and then the third method is the using the definition of a derivative to get the momentum operator.
But which one is more accurate? Like which one I should trust more? Because they're really very different, right? They don't really agree.
That I would say. That I'm not 100% sure, but if you look at the overall trend, except for when we just look at the half cell, so when we just compute the electron on the other side where you think combination would happen, they're still, this line is very low, but they still have a minimum, so they are relatively consistent. Even though the trends are, the quantitative trends are a bit off.
Okay.
And through this, we can look at the time evolution of the potential and the electron, and we see a very interesting change in the potential as we increase our dielectric constant, where we see a very, very dramatic change in our potential when we have a dielectric of 1. This is due to having the hole go back and forth in the potential well, which can increases the potential back and forth, and we see that even when we go to 4, but when we go to 80, it's pretty much constant. And then the electron probability, we can see that at 4, there is a definite localization, where at 1 and at 80, it starts to become more delocalized, which this also supports the idea that the electron is staying on the iron versus recombining. So in conclusion, we see that when we vary the dielectric constant, if it's very high or above 10, the rate of recombination is higher than when it's lower, and this is an image of the recombination at when we do 1 dielectric constant. And our conclusions also support the paper where they say that a polymer matrix increases the efficiency of the cell. Future work for this would be to try and go in 2 dimensions instead of just 1. But on a desktop computer, that's too expensive. So with this, are there any questions?
Okay, let's thank Levi for the input. And until 2, we have a generous 7 minutes to ask him any questions.